You know, we spend a huge chunk of our lives at the office, but do we really get what's floating around in the air we all share? It's actually a lot more complex than you'd think. So let's break down the hidden science of what's really happening between those cubicle walls.
So, we've all had it drilled into our heads, right? Stay 6 feet apart. It's become this golden rule. But what if I told you that inside a closed office, that 6-foot bubble, it can be pretty much meaningless? Let's dig into why that rule just doesn't always add up.
Okay, this right here, this is the one thing you need to remember. Just picture it for a second. If your coworker suddenly lit up a cigarette at their desk, would that smoke just stop, like politely at a 6-foot line? No way. It would drift, it would spread, and before you know it, it's everywhere. Well, viral particles, they work in a very, very similar way.
So, you might be asking, where did this whole 6-foot thing even come from? Well, it was based on these big, heavy droplets from a cough or a sneeze, the kind that fall to the ground pretty fast. But see, that's not the main way viruses travel indoors. The real carrier is way smaller, and it doesn't really fall, it floats.
And that brings us to the real culprit, aerosols. These things are microscopic. They're so incredibly light that they just hang out in the air. They can ride the currents from the air conditioning, or even just from someone walking by, and they can linger for a long, long time. Just like that cigarette smoke we talked about, they build up in a room's air, which makes your exact distance from someone a lot less important.
Okay, so if these tiny particles are just floating around everywhere, what's our first line of defense? Well, it's gotta be the mask on your face. But here's the thing the data makes super clear. Not all masks are even in the same league. The differences are actually pretty staggering.
And look at this breakdown. The difference in protection is just, wow, it's huge. An N95 is the gold standard because it's literally designed to filter out those tiny aerosols. A surgical mask, it's way better than nothing, for sure, but a ton of air leaks in and out around the sides. And a simple cloth mask? Well, it's really just stopping the big droplets, not the tiny aerosols we're worried about.
And it's not just about the mask material. It's actually a two-part equation, filtration and fit. Filtration is all about the quality of the fabric. Can it stop the particles? But fit, you could argue fit is even more important. I mean, what's the point of a super high-tech filter if all the air you're breathing just sneaks in through the gaps on the side?
Wow, okay, and this chart just makes it crystal clear, doesn't it? Look at that jump. You go from a cloth mask, which might stop about 1/3 of the particles, all the way up to an N95, which gets almost all of them. When you're dealing with aerosols, the quality of your mask just matters. A lot.
All right, we've talked about what you can wear on your face. But what about the room itself? The air everyone in your office is sharing, it's like an invisible highway for viruses. And your building's ventilation system? That's the traffic controller. How quickly that highway gets cleared is a really critical piece of the puzzle.
Now, this next idea is a real game changer. In a room that doesn't have good ventilation, time is not your friend. Those aerosols just build up and up and up. This means that spending 8 hours across the room from someone could actually be way riskier than spending, say, 15 minutes up close in a room with a constant flow of fresh air. It's not just about distance, it's about time.
So how do we actually measure how clean the air is? Well, there's a metric for that. It's called air changes per hour, or ACH for short. And it's pretty much what it sounds like. How many times, every hour, does the room get a complete refresh with clean air from outside? That number tells you how fast the bad stuff is getting flushed out.
And you're probably wondering, okay, so what's a typical office like? The answer? Well, it's about 2 to 3. That's it. Which means a lot of the air you were breathing an hour ago is probably still floating around you right now.
But now, let's put that into perspective. Compare that to a place where air quality is literally a life-or-death matter. A hospital isolation room? We're talking 12 or more air changes an hour. That is 4 to 6 times better than a standard office. It really shows you just how big the ventilation gap is.
All right, so we've covered the air. But what goes up must come down, right? Those viral particles eventually land somewhere. And when they do, they create another sort of hidden danger. Contaminated surfaces, or what scientists call fomites, that can stick around long after someone has gone home for the day. And how long a virus can survive really depends on where it lands. It's pretty fascinating, actually. On porous stuff like paper or cloth, it tends to dry out pretty quick, usually within a day. But on those hard, non-porous surfaces, think about your plastic keyboard or the stainless steel coffee pot, a virus can stay viable for 3 to 7 days. That's a long time.
Okay, I know. We've talked about aerosols in the air, viruses on surfaces. It can feel like a lot. But the good news is there's a simple, logical way to think about solutions. We can organize them into a clear hierarchy. This is your action plan, ordered from the most effective thing you can do down to the least.
And here's how that action plan breaks down. It's all about this hierarchy. Number 1, clean the air for everybody. That's ventilation and filtration. It's the most powerful tool. Number 2, protect yourself with a high-quality, well-fitting mask. And finally, number 3, clean the high-touch surfaces in the space. Clean the air, protect the person, then clean the space.
And all of this really leads us to one big question, doesn't it? We design our offices for productivity, for collaboration, maybe for comfort. But after everything we now know, it's worth asking ourselves, have we actually designed them to be safe? It's just something to think about the next time you walk through those doors.